Good morning to Dr. Shafirah. Here is our integrated project. We are from Group 6 and our group members are Najmi, Amanda, Joyce and Zafirah. This integrated project encourages us to apply the knowledge we learned in thermodynamics. We need to determine the amount of heat required to run the pressurized water reactor and efficiency of the nuclear power plant. Nuclear power plant is a type of power plant that uses nuclear fission process in order to produce electricity. In nuclear power plant, the heat produced in the reactor core is utilized to boil water into steam. This turns the blades of the steam turbine. The turbine is connected to the generator that produces electricity. After that, nuclear plants cool the steam back into the water in a cooling tower. We are required to find out how a nuclear power station works and how much heat is generated. Rankine cycle is used in nuclear power plants. The Rankine cycle is a model used to predict the performance of steam turbine system. It was used to study the performance of the steam engine. The Rankine cycle is an idealized thermodynamic cycle of heat engine that converts heat into mechanical work. It is also an idealized cycle in which friction loss in each of the four components are neglected.
The actual process that happens in the nuclear power plant can be simplified into this schematic diagram and divided into left side and also the right side of the process. Here at the left side, water which acts as a working fluid will flow to S1 as compressed liquid at 15.5 megapascals, 275 degrees Celsius into the pressurized water reactor and comes out as a compressed liquid at 15.5 megapascals and 316 degrees Celsius. And then the water will flow to the tube of the steam generator to exchange heat with the right side of the cycle and comes out as a compressed liquid at 15 megapascals. And then the liquid will flow to the reactor cooler pump through S3, where here the pressure of the water is brought back to 15.5 megapascals and thus completing the left side cycle of the process. As for the right side cycle, the fluid will flow through R2 as in saturated mixture at 8 kilopascals into the condenser and comes out as a saturated liquid at 8 kilopascals. And then the fluid will flow into the pump where it being compressed into compressed liquid at 6 megapascals and then flow into the shell part of the steam generator and comes out as a superheated vapor at 6 megapascals, 284 degrees Celsius. And then the steam generator also connected with turbine to produce the amount of work of 3000 megawatt as per requested by question. And other than that, the condenser also connected with stream T1 and T2 to exchange heat with stream R2 and R3. And this part will be discussed further in the PhD part.
Hi guys, I'm Joyce and I'm going to explain about the power generated by PWR in our nuclear power plant. These are the assumptions used in our calculation. We will do the calculation of the right side and left side separately. For the right side, it is its schematic diagram, and this is the TS diagram of the Rankine cycle for the right side. For R1, the pressure is 6 megapascal and temperature is 284 degrees Celsius. In table S6, through interpolation, we can get the value of H1 and S1. For R2, the pressure is equal to 8 kilopascal and temperature is equal to 41.4 degrees Celsius. In table F5, through interpolation, we can get T2, X2, and H2. For stream R3, the pressure is equal to 8 kilopascal and temperature is equal to 41.4 degrees Celsius. It's in compressed liquid state and we can get its H3 and V3. Then we will do the energy analysis for each component. For turbine, we substitute the value into this equation and we will get the mass flow rate of the right side is equal to 3127.05 kg per second. The mass flow rate for the right side is constant throughout the loop, which is 3127.05 kg per second. For pump, we substitute this value into this equation and we will get the value for H4. For steam generator, we substitute the value into this equation and we will get the Q in is equal to 8255.412 kilowatts. And we can calculate the value of N, which is equal to 0.36. Then we will do the energy analysis for the left side, S1, S2, and S3. For S1, the pressure is equal to 50.5 megapascal and temperature is equal to 275 degrees Celsius. It is in compressed liquid state, so we can get the value of H1. For S2, the pressure is equal to 15.5 megapascal and temperature is equal to 315 degrees Celsius. It's in compressed liquid state too, so we can get the value of H2. For S3, the pressure is equal to 15 megapascal. It is in compressed liquid state and we can get the value of V3 too. Then we will do the energy analysis for each component. For steam generator, we substitute the value into this equation and we can get the mass flow rate. For pump, we can substitute the value into this equation and we can get the value of H3. For PWR, we can substitute the value into this equation and we can get the value of Qin is equal to 8,286.43 megawatt. And we can get the heat generated for PWR in 24 hours, which is equal to 715083552 megajoule.
Lastly, we have to calculate the actual power produced for the pressurized water reactor. And to calculate the actual power, we have to assume the thermal efficiency of PWR, which is 33% and equal to 0.33. And to get the work net out, which is the actual power produced, we can use the formula of thermal efficiency, which is equal to work net out over Qin. The Qin is the heat generated for PWR that we can get from the previous slide, which is 8,285.43 megawatt. And after we key in the value, we will get the work net out, which is 2,754.19 megawatt, which is equal to actual power produced. And to calculate the percentage error, to compare the theoretical value, which is 3,000 megawatt, and the actual value, we will get the percentage error is 8.86%, which is below than 10%. That's all from us. Thank you.